The forbidden hole, star explosions and the limits of black holes.
In the universe, giant stars end their lives in dramatic ways, often leaving behind black holes.
However, there is a mass range where these black holes simply shouldn't exist, a forbidden hole between about 50 and 130 solar masses. A new study published in the journal Nature has provided clear evidence of this mysterious gap, based on gravitational waves detected since 2015. It all begins with the evolution of massive stars. For most of their lives, a star maintains a balance between the pressure generated by nuclear fusion in its core, which pushes it outward, and the force of gravity, which pulls it inward. When the nuclear fuel runs out, the core collapses. For stars with intermediate masses, this collapse forms a black hole. But for extremely heavy stars, between 50 and 130 times the mass of the Sun, something different happens. In these stars, the core reaches such high temperatures and pressures that gamma rays interact with atomic nuclei and create electron-positron pairs. This particle creation steals energy from the radiation, reducing the pressure that sustained the star. The result is a partial and violent collapse, which triggers uncontrolled thermonuclear reactions. The star explodes completely in apparent stability supernova, an explosion so powerful that nothing remains, not even a black hole. It's as if nature itself erases the possibility of forming a remnant in this mass range. Astronomers call this interval the gap, or forbidden hole, because theory predicts that black holes formed directly from solitary stars should not exist between 50 and 130 solar masses. Below 50 solar masses, black holes form normally. Above 130, other processes may allow formation, but observation shows that black holes above 45 solar masses are already rare.
The proof came from gravitational wave astronomy. Since LIGO and Virgo began detecting black hole collisions, scientists have accumulated hundreds of events. Each detection allows for precise measurement of the masses of the two black holes involved in the merger. Analyzing this data, a team led by Hui Tong of Monash University in Australia found something revealing. The gap appears clearly in the masses of secondary black holes, the smaller of each pair, but not in the masses of primary black holes, the larger ones. This makes sense. Secondary black holes are usually pristine, meaning they are formed directly from individual stars without having undergone previous mergers. Primary black holes, in some cases, can be the result of hierarchical mergers when two black holes have already merged before and then joined with a third. These black holes built by successive mergers can spin faster and occasionally fall within the forbidden range, explaining the few cases observed in this region. The study confirms that parent stability supernovae do indeed occur and shape the black hole population in the universe. At the same time, it raises new questions. How often do these total explosions occur? How efficient are mergers at filling the forbidden hole? Why do we still see some black holes in this range, even if they are rare? Understanding this forbidden hole is fundamental to modern astrophysics. It directly connects the ultimate fate of massive stars with the gravitational waves that traverse the cosmos. With more sensitive detectors in the future and more recorded events, scientists will be able to refine models of stellar evolution and discover if there are other mechanisms at play.
In short, the universe does not allow black holes of certain masses to be born directly from solitary stars. Thanks to nature's most violent explosions, there is an invisible boundary that most giant stars respect when they die. Observing this gap through the ripples of spacetime helps us better understand how the cosmos builds its most extreme objects.